It's 5 o'clock. It's all about time. So we start on the top of the hour exactly now about the next webinar about rapid reaction monitoring with mid-IR dual-com spectroscopy. We have also a live demonstration. My name is Florian Eigenmann. I will be your host today. My colleague Raphael Horvath will guide you through the live webinar a little bit later. So I start with the introduction and the review of previous applications, and also an overview of IRIS F1, the first commercial available dual-com spectrometer. Then we have the demonstration of a stop flow reaction with 440 spectra per second. I will dive in a little bit in the results of those stop flow measurements and line out the acquisition time. Then, as I said before, the live demonstration of real-time curing monitoring, which will be the body of that webinar. And we end up with questions and answers with special guests today. So the benefits of IRIS F1 is, besides high speed, is high resolution, which was reported earlier, then the broadness, parallel multi-wavelength acquisition, and also high brightness. So in this webinar, we specifically will focus on the speed advantage and outline reactions in millisecond time resolution up to even down to microsecond time resolution. This was reported earlier in single shot, sub-microsecond mid-IR spectroscopy on protein reactions. You acquire not just a single line, so you acquire several lines actually, up to 200 lines with a span of 60 to 100 wave numbers. You can see here such a multi-heterodyne signal, and those gaps which you can see here, those are really absorption information. I lined up once actually those information with a water vapor hydron information, which gives really nice, which corresponds really nice with those information in the order of, also in the range of the 1650 laser. The first dual-com spectrometer, IRIS F1, which is commercially available, is a complete system, which has actually also the possibility to exchange laser modules. So you can see that here on the following pictures. So those replacements of those laser modules are crucial, so you can switch between different applications in a few minutes and then let them stabilize for probably 30 minutes. We are very proud about the laser availabilities today. We have already up to 8 lasers in stock. So you can see here on the side, we have lasers specifically at 1600, 1675, 6050, 6025, 1300, specifically to measure amide 1, carbonyl bands, but also at the lower end. Basically, all those lasers between 2200 and 900 would be available. I will not go into other applications, as we have seen already several applications before. We had some webinars, a few of them here. Joachim Heberle, one of our customers, had a webinar about protein dynamics, about also reaction monitoring, single shot measurements. Then we have also somebody here in the audience, a very big name, Ron Hansen. He mentioned actually, or he did some measurements there in that group about combustion diagnostic. Nico Pinkowski did already a webinar there. Then we had an early webinar with Ted King about stop flow measurements. We have customers in microfluidics, and then Ian Birch's also a webinar there, and even a paper about spectral electrochemistry. It was even talking about the paradigm change in infrared spectroscopy. Then earlier we had also 2 high-resolution spectroscopy webinars. One was with Muriel Lepere, just recently, and also Lukas Emenecker in high-resolution spectroscopy. The setup for the next measurement about stop flow, that you have a little bit an outline before we dive into, is the setup here of the IRIS F1 with the stop flow setup from TGK Scientific. There is actually calcium fluoride transmission cells with a path length of 100 micrometers. The background acquisition is done on pure solvent in that case. and the triggering is very easily done. We did it sometimes manually, but you can do that directly and trigger that also automatically. Before I hand over or introduce also Raphael, one of my colleagues here, I want to go over the reaction scheme of the stop flow measurement at 1620. This hydrolysis of this ester is presented in the following scheme. So we were using a methyl chloroacetate. I mean, this is a kind of a test reaction, which is used for several demonstrations earlier, before. Then using of FTIR spectroscopy was just limited to time resolution. So this reaction proceeds as follows. We were using also sodium hydroxide, and then it ends up in his salt and methanol. The whole thing was done in D2O. So the introduction of Raphael, he received his PhD in Raman spectroscopy at the University of Otago in New Zealand. Then he served as a research fellow at the University of Nottingham on the supervision of Mike George, and is already almost 3 years application engineer at IRSweep. So yeah, we go to the first measurements which we have done.
So today I want to show you two demonstrations. The first one is a stop flow demonstration using the SF73 stop flow system by TGK Scientific. It's based on two syringes which are pumped at the same time. So on the left we have methyl chloroacetate, on the right we have sodium hydroxide. Florian just showed you the resulting reaction from this mixture, and what happens is that both solutions are injected into a mixing chamber just before the sample cell, and then the flow is stopped, which means you have a steady state condition and you can measure the kinetics and the evolution of the reaction. And that's exactly what we're doing. So the laser beam comes from left to right, and it probes the reaction volume, and we will record this on the IRIS-F1. Now the IRIS-F1 is triggered through the SF73 stop flow system, meaning we don't need to worry about trigger timing or anything like this. It knows when to start the measurement. So let's do this. I will press the sample button. You can see the heterodyne signal, which shows the spectrum of the laser essentially. It freezes and it waits for a trigger input. And the trigger input comes when I press the fire button. Now I've set it to take 500 measurements, and it took a little bit more than a second. So you can see it's now counting down the buffer from 500 down, and this is as the measurements are being processed. One of the reasons we're doing this video is to show you how much faster this instrument has gotten since we started this about 18 months ago, where we did about, I think, 25 spectra per second, and then we increased that to 40, increased to 200, and now we're at just under 500 spectra per second. And this is really useful for stop flow measurements like this, because in principle you can measure for as long as you want. So you can keep measuring, maybe not at this high rate, but you can measure for minutes and hours if you really wanted to. It's also different from the other measurement mode that we have, which is the time resolved measurement mode, where you can measure 1 million spectra per second, but you can only do this for about 30 milliseconds. So there are different modes for different applications, and this one we think is particularly well suited to this millisecond to minute scale reaction monitoring that we're doing here. So what we're doing now is we're just waiting for the buffer which is filled up to start to finish processing, and then we can load up the files and actually look at the reaction that we just did. So I will do this now. So I will start by copying the file. And we have a script here which all it does is it opens the file and it plots the resulting spectra. So there are a lot of spectra, well, 500 spectra, so it takes a little while to do. And here you can see the result. So you have methyl chloroacetate breaking down, and it forms this band. So the product is shown here on the left. These big spikes, they're actually due to water lines in the atmosphere. So this is just natural absorption because we're not purging the instrument. But they can be removed in post-processing very easily. And Florian will soon show you what it actually looks like when you spend a little bit of time processing these spectra. So this the product of the methyl chloroacetate hydrolysis shown here. If we want to know what the kinetics are for this process, we can pick a point and plot it. So let's pick about 1595 wave numbers. And this is the resulting kinetic curve. So you can see even here at very short times, so this is 200 milliseconds here, we have quite a few data points in there. And I should also stress they're not just data points, they're actually full spectra. You can really look at each individual spectrum and see what happens if there are any intermediates or anything else that you might want to know about. So yeah, I hope you like this first of the two demos, and yeah, we'll do a second one soon.
Thanks, Raphael. We go directly into the results, and before we do the curing live demonstration, I will point out a little bit how we get those really nice reaction monitoring with 440 spectra per second, or even faster. So, as Raphael already mentioned, those are the water vapor correction which we just applied here, and you see here that we get at 1604 wave numbers down to 1 second, really nice kinetic traces. And I do just the same as Raphael did just before, zoom in a little bit here at the beginning to 0.25 seconds. And as he already mentioned, we get a lot of spectra here and a really nice signal to noise ratio. And this is done without any chemometrics. Going into a little bit more, specifically this chart is a software update we recently have done at IRSweep. It shows the acquisition frequency versus the acquisition length. And this is actually based on a logarithmic scale. And you see just before the lockdown, and we reported that earlier already, Raphael mentioned that already, we had around 200 spectra per second, 220 spectra per second, and we doubled the rate, which is the paradigm change in time-resolved spectroscopy for non-repeatable reactions when step scan FDR, for example, is not applicable. Go a little bit closer or even more down in the microsecond time regime. We have that as well. You see here for some applications like in the combustion industry where you want to do in a shock tube some analysis, you want to go even faster. So you can see here microsecond time resolution. So we have here even average for microsecond time resolution. This gives now here 33,000 spectra in 130 milliseconds. And like this, it was very nicely done. We could actually get a lifetime of 46.6 milliseconds. So we're using the same reaction, but you see we get a lot of information, and we have also the possibility to even go for even faster reactions by, for example, heating up the reaction or use other pH range. Raphael mentioned that already about the story we have created here, and we are very proud. I'm also very proud to be part of it. As earlier mentioned, we can actually go to the technical limitation in 1 million spectrum per second, and this is already published, as mentioned before, by in the group of Ron Hansen and also in the group of Ian Burgess at the Canadian Light Source with a spectroelectrochemistry application. So now we go to the live demonstration. I hand over this directly to my colleague. Great, Raphael.
Thank you, Florian. So yeah, for the second demo, we will do some photochemistry, namely a curing reaction. We have some UV active glue. So this is used in the semiconductor industry to bind different components together. And it cures very fast if you irradiate it with UV light. So this is what we'll be measuring now. And we will do this in an ATR configuration. And I'll go through the details of the setup. So first I will apply the glue. This is kind of, so this is the ATR prism. I will talk about this in a bit more detail later. This is kind of a low-tech way of applying. I will really just put some glue on this prism. We don't need much. And the holder for this prism is installed in the sample compartment, so the beam reflects up, comes back down, and then is detected here. You can see that up close up. Then the other thing we have is a fiber optic source, which is connected to a mercury lamp, which will provide us with UV light for the shutter. So for this experiment, we will trigger everything manually, meaning I will just press sample on the instrument, and Florian will push the shutter button for me. Because we are working with UV, at this point, everybody please put on their UV glasses. So then we can start. Are you ready, Florian?
I am armed, ready to go.
Go. So I took 1,000 spectra there, which at the same rate as earlier. So this took a little bit more than 2 seconds, which is why we had to be quite precise with the timing. You can turn it off again. And what you can see here, and hopefully this also will be reflected in the spectrum. So while we wait for the processing, I'll tell you a little bit more about the equipment that we use. So we use silicon ATR crystals manufactured by a company from Munich called Irubus. They're quite neat. So silicon, in my opinion, is a little bit of an underrated material for ATR, but it has some very advantageous properties. So compared to zinc selenide, it is non-toxic and a little bit more durable. And compared to calcium fluoride, you can measure to much lower energies. The downside typically is that it has quite low throughput because silicon is just not so transparent to IR. The way Irubus fixed this, you can see here, the crystal is very thin, so this is suitable for spectroscopy with an FTIR. But even more so, if you have a laser, you can just turn up the power. So if you have any if you have slightly too much absorption by the crystal, you can very easily overcome that. Furthermore, you can kind of see this microstructure down here. Hard to see. This is designed to eliminate fringing. For laser instruments. So it's actually a very good match for this instrument. Secondly, we should also thank another Bavarian company called Delo, who manufactured the glue, which allowed us to do this demo today. So we're almost through with processing. Like I said, it's much quicker to acquire than it is to process. So we acquired 1,000 spectra in a little bit over 2 seconds here. And the workup just takes a little bit longer. But once it's done, I will load the file, and then we can see if hopefully we captured the curing process nicely. So I will start copying the file. The file name. So we're using the same script as earlier, and very similar data analysis scheme. So we're just plotting all the spectra.
And once we're waiting, you can actually use the chat box, question and answer, and put already your questions and answer in there. We will address that at the end of the live demo, by the way.
So this is the result. So you can see there's a band disappearing at around 1655 inverse centimeters, and a band appearing at about 1630. It looks like there are even two bands in here, which you can see quite nicely. So we have a base resolution of about 0.3 inverse centimeters, and in this graph it's been averaged to about just under 4 inverse centimeters. So there's a little bit of spectral averaging, but for solid state samples like this, it's very easy to get away with this. So we can also plot the kinetics to see how many points we really have. And so I will plot at 1630 and 1655, like I just mentioned. And these are the kinetic traces for this reaction. So you can once again zoom in. Each point on here, and yeah, there are 1,000 points in this entire range. Represents an entire spectrum that you can look at. We can also look at the individual spectra. Then we can step through the evolution, basically, of what we're seeing. But also, it gives you an idea of the signal to noise that you can expect from a single spectrum in this, because it's nice getting these kinetics, but that tends to be easier than actually getting usable spectra from a single point. So, considering we have 1,000 spectra here in this 2-second time interval, I'm going to pick 100, 200, 300, and 400. So just these numbers. 100, 400. And so we end up with 4 spectra, each of them corresponding to a total acquisition time, so a total integration time of half a millisecond. So yeah, this one is done at 0.2, 0.4, 0.7, and 0.9 seconds, and you can quite nicely see the progression. So this is a level of signal to noise you can expect from a single acquisition. And the signal isn't huge here, so I mean it's 0.1 absorbance units. So I'm quite happy with this. If you would like to see anything else in here, so if you would like me to show you anything in particular, then please let us know in the question and answer session. This is actually a good place to start the question and answer session. I will put my mouse on because we'll move closer together, I think.
Exactly. Yeah.
And in fact, there was a question which we got from an earlier webinar, which we did with Ted King. And the question was, the stop flow instrument that we showed had 2 syringes to drive 2 different reagents. What about a third syringe? And it just so happens that we have Ted King in the lab today, so he showed up kind of unexpectedly, and he can probably give a much better answer to this question than I can. So welcome, Ted.
Thank you. That's a special guest. That came from the UK.
Hello. It's good to be here. Thank you. So we have gone ahead on the back of that webinar back in April, and we've designed the extra reagent line in. So we've got the umbilical assembly with the transmission cell at the end here. This is much the same as we have on the 2 reagent instrument. But we've added the 3rd reagent line, and hence the 3rd port in the mixer. And as you can see at this end, we've got the valve in the middle station here. So we've now got 3 reagent system built. We haven't done much with it. The main thing is it's taken a ride from Frankfurt on Avon in the UK to Zurich.
Yeah, so it's in the works.
It's in the works, yeah. And we'd like to get some work done with it over the next few weeks and months. So we talked about the type of reactions that we could do with it. One idea is that sometimes you want to do a reaction where the conditions for the reaction don't provide the stability for the reagents. So the idea is that, say, you could do a pH jump at the mixer by introducing a different buffer from that third reagent. You could also use it to change the mixing ratio, of course, by mixing 1 against 2 or just 1 against 1. So that's some ideas that we've had inspired by that question.
Thanks, Ted. We have already a few questions coming in. For the Q&A session, as I mentioned earlier before, just type in your questions. And we try now to answer all of them. I have a question for Raphael. You mentioned waterline removal in post-processing. How does that work?
Yeah, that's a good question. So you probably noticed that there were kind of blocky sections that were referred to as waterlines. Of course, waterlines are much narrower normally. The reason it looked like this is because we also did spectral averaging. So we went from 0.3 reciprocal centimeters to about 3 to 4 reciprocal centimeters, and that sort of smears out the waterlines a bit. The actual waterline removal, though, is very simple. You just have to pinpoint which lines are the problem and take them out. This is much easier compared to, say, an FTIR system, because in FTIR you apodize, and you just by doing this, you have to apodize. You tend to smear out the lines a little bit. So neighboring lines are affected by each other. So you just pick out one point and remove it. You will still have quite a lot of interference from neighboring lines. But we're fortunate that this isn't the case here, because we're probing at 0.3 reciprocal centimeters, but each line is actually very narrow. So if we remove one line, it really removes the waterline. So that's all I did. I just removed, in this case, actually six different points, which decreases the resolution very slightly, but it actually removes any artifacts that you're confident about, like water, quite effectively.
That's a good one from the resolution, actually. I just would have another question here. What is the maximum spectral resolution you can achieve? Here with 220 or 440 spectra per second.
So if you're going at this speed currently, I would say about 0.3 reciprocal centimeters. If you're willing to go slower, then I would recommend actually looking at the webinar of Muriel Lepere. There it was, I think, showing quite nicely that you can fill in the gaps. So you have these lines which are very narrow, and this space, there's nothing in between. You can move them around and probe all the in-between points. And in that case, you can get to below 1 times 10 to the minus 3 inverse centimeters. So that's been shown there, but you do sacrifice time resolution on that.
Okay. There's a question actually just coming in on the chat. Is it possible to use an optical fiber to avoid those water lines? And or do you recommend simply using Hydron to remove them after the measurement?
Yeah, there are a few measurements. So optical fibers are a possibility. Yes, you can do that. Actually, the simplest way to do it would have been for me to build a patch. So for me to close the lid, it obviously would mean drilling a hole in the lid so the fiber can go in, and then just plugging in nitrogen and cleaning out the air in the spectrometer. That works very well, but for this demo, I didn't want to drill a hole in the lid. So that's one way of doing it. As for using Hydron, that's actually a very good idea, but it's actually not strictly necessary, because one thing that you get from the data output is a distribution of standard deviation per line, and so it's very easy to see which lines are noisy and which lines are not noisy, and based on what's noisy, you can just cut out noisy ones and discard them, and they are 9 times out of 10 the water lines, because there are no photons at those points.
I have a question actually also for Ted King about what kind of chemistry, you outlined that already, what kind of chemistry would you do with the 3 mixing device? That you can mix 3.
Well, another example would be if you wanted to, say, flush out in between running shots with it, running reactions, then you could simply have a buffer in there to clean through and retake baselines. But other than that, to say, it gives opportunity to put additional volume in, so you can push 2 lines against 1, and of course you can do things with different size syringes to enhance that.
Let's see, and then there was another question: why is the signal to noise so much higher than in FTIR, specifically in this time
Specifically
axis
for
problem.
this, these tend to be photon limited type reactions when you're working with FTIR, because you're using a glow bar source, so you just don't get enough photons to really probe what you want to see. That's one thing. So we have a laser instead of a glow bar source, so we get as many photons as we want. And the second reason is at the speeds that we're measuring, which is about 2 milliseconds per spectrum, you really can't move the mirror fast enough anymore either. So
no movable parts.
so yeah, there are no movable parts here exactly. And if you do this with a rapid scan, you can do things like interferogram splicing and techniques like that, but they tend to be difficult to do. I mean, it's very challenging. And my hat's off to people who do this, but it's not so easy.
Thanks. Then there was a question: was the demo really live? I mean,
Was the demo really live? I mean, this one is live. You can see me.
7031.
You can see me answer the questions. The first one obviously was pre-recorded. We couldn't take this stuff away and replace it with the second setup in the course of 5 minutes. But yeah, it was done very recently.
Yeah, I just want to summarize. I mean, we will be here. We will be ready for additional questions. I want just to outline. We will continue with those webinars. We have a very important webinar coming up on the 15th of October. That will be with Sharon Theist. We will talk about recent latest developments in QCL frequency comms. So if you find that interesting as well, please sign up for that. And if you have additional questions, also just shoot us an email or go on the page www.irsuite.com. Thanks for watching and all the best.
Thank you.